So in the past couple of videos, I've introduced this idea of parameterized curves, where instead of representing a graph with a single equation, we represent a graph with two separate equations. We involve an extra variable, a parameter, typically the letter t, and we define the x and y coordinates on our graph in terms of equations involving that parameter, which is kind of wild and way more powerful than you probably realize right now. But we didn't really get far enough into it for you to kind of see the power of parameterization. What we did learn is how to go from the standard form of an equation to a parameterized form of that equation, and from the standard form of the equation to a specific parameterization of the equation, and how to go back in the other direction, how to go from the parameterized form to the standard form. And you're like, yeah, I learned all those things, and I guess I was able to follow, although I don't really understand why I was learning it. I mean, one question I might have is, why am I learning it now? What's this have to do with trig? Well, it turns out we've already done parameterization in this class. This isn't a new topic. It's just a new way of thinking about something we've already done. We defined this function, the cosine of t, to be equal to the x coordinate on the unit circle at an angle of t. And we define the sine of t to be equal to the y coordinate on the unit circle at an angle of t. But really, if you don't think about that, if you just think about this as equations, this is a parameterization. The x coordinate is given as an equation of this parameter t, and the y coordinate is given as an equation of that same parameter t. Instead of thinking about t as an angle, we can think about t as time. We can keep track of where some particle would be by noting its x coordinate and its y coordinate at various times. So at time 0, for example, if we want to know what the x coordinate would be, what we do is we change all the t's into zeros here. The cosine of 0 is equal to 1, so the x coordinate of this particle should be at 1 at time 0. And since the sine of 0 is 0, the y coordinate of the location of this particle at time 0 should be equal to 0. What I'm saying is if we wanted to know the graph that these parameterized equations represent, we'd have to make sure that at time 0, the particle had an x coordinate of 1 and a y coordinate of 0. In other words, it's right here. And we could do that same thing at time 1 and time 2 and time 3 if we want. Although I don't really want to pull out a calculator and figure out what the cosine of 1 and the cosine of 2 and the cosine of 3 is. So maybe it makes more sense to take time intervals like pi over 2 and pi and 3 pi over 2, for example. And if you figure out the corresponding x and y coordinates and plot those on our graph over here, we see that at time pi over 2, we're up here with an x coordinate of 0 and a y coordinate of 1. And at time pi, we're over here. And at time 3 pi over 2, we're down here. And if you had tracked a bunch of points in between, what you'd see is the particle is tracking out this circle centered at 0, 0 with a radius of 1. Oh yeah, the unit circle. If we switch our perspective and instead of thinking about t as an angle, we think about t as time, you can kind of imagine a particle that's traveling in this direction around the unit circle, taking a time of 2 pi to do a full lap. Really, all this set of equations is a parameterization of this equation, x squared plus y squared equals 1. The different x and y coordinate pairs that satisfy this equation are all the points around the unit circle. And one way we can parameterize that equation is by letting our particle start here and travel in a counterclockwise direction, taking a time of 2 pi to get around the circle with this parameterization right here. There's lots of different parameterizations of the unit circle. This is just the one that we've seen before in our class. I think that's kind of cool. It gives this whole new perspective of everything we've been doing in this class. In the previous videos, we've learned how to go from the standard form to the parameterized form and how to go from the parameterized form to the standard form, right? If you want to go from standard to parameterized, well, it's fairly easy as long as you don't care about the parameterization that you're doing. We can just pick one of the variables to be equal to t, and then plug that in to create our other equation in the parameterization. And if you want to go from parameterized to standard, you just solve one of the equations for that parameter t, and then plug that into your other equation to change the two equations into one. We can do that same thing down here. We can go from this parameterized form to this standard form, or from this standard form to this parameterized form. Although what you'll see in this video is it's a little bit more challenging than it was in the previous videos. First, let's go from parameterized to standard. So let's start out with x equals cosine of t and y equals sine of t, and let's see how we can change those into this equation. Well, if you think about how we did this in previous videos, we solved one of these two equations, it didn't matter which one, for the variable t. Can you do that here? Yeah, absolutely. If x is equal to the cosine of t, then t is equal to the arc cosine of x. Then what we did is we took our other equation, and instead of writing the parameter t, we substituted in what t was equal to. So we would say that y is equal to the sine of, and then instead of writing t, I could write arc cosine of x. What we've done is we've gone from these parameterized equations to this single equation. And in this single equation, we represent y in terms of x. So we're done? Well, kind of. The problem is this doesn't look like what we expected it to look like. The reason this doesn't look like we expected it to look like is because this is not simplified. But this equation is the exact same as this equation, and I'm going to show you how to simplify that to come up with this equation. The way that you simplify it is you take advantage of something that we learned like a month ago. Anytime you have an inverse trig function nested inside of a trig function, you can simplify it. The trick that we learned was a substitution trick. We let t be equal to the arc cosine of x, whatever the inverse trig function was. Because if t was equal to the arc cosine of x, then instead of thinking y is the sine of the arc cosine of x, we can think that y is just the sine of t. And because t is the arc cosine of x, we know that the cosine of t is equal to x, which we learned to write as x over 1 because writing it as a fraction made it easier to draw the picture. The picture was a right triangle with an angle of t down in the bottom left corner here. And because the cosine of t using SOHCAHTOA is the length adjacent divided by the hypotenuse, we can label this side x and this side 1. Remember, our goal is to simplify the sine of the arc cosine of x, which is the same as the sine of t. So if we can figure out the sine of t from this picture, we will have simplified this original expression. The good news is we can figure out the sine of t from this picture. Sine is opposite over a hypotenuse, so we just need this last side length. But no big deal, if you have two side lengths in a right triangle, you really know all three of them. Maybe you call this side length, I don't know, the letter b, and then using Pythagorean theorem, x squared plus b squared is equal to 1 squared. Think a squared plus b squared equals c squared. So x squared plus b squared equals 1. B squared is equal to 1 minus x squared. So b is equal to the square root of 1 minus x squared. Technically plus or minus, but because we're talking about side lengths, we can leave that off and just say b is the square root of 1 minus x squared. Now that we've solved for all three side lengths, we can take advantage of this picture to rewrite the sine of the arc cosine of x, because the sine of the arc cosine of x is the same as the sine of t, and the sine of t, according to this picture in SOHCAHTOA, is the opposite side divided by the hypotenuse. So y is equal to the square root of 1 minus x squared. Using this clever method that we learned about a month ago, we're able to simplify this equation as this equation. Remember, this equation came from taking the parameterized forms and eliminating the parameter t to get an equation for y in terms of x. We've now simplified that to get y is equal to the square root of 1 minus x squared. And if we manipulate this a little bit, maybe square both sides of the equation, we get y squared equals 1 minus x squared, and then add the x squared to the other side, we get x squared plus y squared is equal to 1, which is exactly what we were hoping to get, the standard form of the equation of the unit circle. We can use the same method that we learned previously to go from the parameterized form to the standard form. The only problem is when we use that method, we end up with an expression that we need to simplify, and simplifying that expression is pretty complicated. We can get there using this inverse trig argument that we just did, and everything works out, but the good news is there's an easier way if you're a little bit clever. If I want to go from the parameterized form to this standard form, I can do so with some really clever algebra and cut out this step in purple. The way I do it is I have to take advantage of the Pythagorean identity. Maybe you remember that the Pythagorean identity tells you that sine squared t plus cosine squared t is always equal to 1 for any angle t. This is an equation that's always true. So what I can do is, instead of taking this equation and plugging it into this equation, I could take each of these equations and plug them directly into this equation. Instead of writing sine squared t, which means the sine of t squared, I can write the letter y because the sine of t is the same as y. So I could write y squared plus, instead of cosine of t, I could write the letter x. And using this Pythagorean identity, I jump straight from these parameterized curves to the standard form that I was hoping for, x squared plus y squared equals 1. It's cool that you can do it both ways. This is the way that's more like the method we learned in previous videos, but this way, starting out with the Pythagorean identity and then substituting in, makes the algebra significantly easier if you're trying to go from the parameterized form to the standard form. What about going in the other direction? What if you started out with the standard form x squared plus y squared equals 1 and you wanted to go to the parameterized form? Well, remember, when we're going to the parameterized form, there's lots of different parameterizations we can come up with. What we learned is if you don't care about the parameterization, then the easiest thing to do is just to pick one of your variables, like the letter x, and make that the parameter t. But what you'll see is that's problematic in this case, because if my x is equal to t, then I get t squared plus y squared equals 1 for my other equation, and when I try to solve this for y, I get y squared equals 1 minus t squared, so y is equal to plus or minus the square root of 1 minus t squared. The fact that this is squared ends up causing problems when I take the square root of both sides of the equation because it gives me this plus or minus. And this plus or minus is preventing me from writing y as a function of t. When I try to parameterize in the same way that I did in the previous videos, I get into trouble because of this plus or minus. Turns out that this is not going to work. You can try letting x be equal to t, or even some other option like x equals t squared, but you're going to run into this issue with the plus or minus. That's unfortunate. Fortunately, we can do something very similar to what we did over here to parameterize this much easier. We're starting out with x squared plus y squared equals 1. But keep in mind that we have this Pythagorean identity that's always true. It's always the case that the sine squared of t plus the cosine squared of t is equal to 1. The fact that I have a 1 here and a 1 here is really nice. I could take this equation x squared plus y squared equals 1, and instead of writing the number 1, I can write what 1 is equal to, sine squared plus cosine squared. Instead of trying to parameterize this equation, I can parameterize this equation, and that'll end up being a lot easier to do. I have to choose equations for x and y in terms of t that satisfy this equation. Well, if I make the x equal to the cosine of t and the y equal to the sine of t, then this becomes cosine squared and this becomes sine squared, and that's definitely going to satisfy this equation, right? Cosine squared plus sine squared is the same as sine squared plus cosine squared. So by changing the 1 into sine squared plus cosine squared, it's easier for me to see this parameterization. It's worth pointing out that this is just one parameterization of this equation x squared plus y squared equals 1. I could, if I felt like it, also choose to parameterize things by letting x be equal to the sine of t and y equal to the cosine of t. That'll also satisfy this equation. What's the difference? Well, this parameterization is one I'm already fairly familiar with. When t is equal to 0, I'm over here. When t is equal to pi over 2, I'm over here. It's a lap around the unit circle, traveling in the counterclockwise direction, taking 2 pi to get all the way around. Look what happens with this parameterization over here, though. When t is equal to 0, the sine of 0 is 0, so my x-coordinate should be equal to 0. And because the cosine of 0 is 1, my y-coordinate should be equal to 1. At time 0, my x-coordinate should be 0 and my y-coordinate should be 1. Sounds like I should be up here. And when the time is equal to pi over 2, because the sine of pi over 2 is equal to 1, my x-coordinate should be 1. And because the cosine of pi over 2 is 0, my y-coordinate should be equal to 0. At time pi over 2, I should be over here. And I can continue to plug in various values of time, and what I'll see is I end up with the same unit circle. It's just parameterized differently. I don't start out at the right and travel counterclockwise. I start out at the top and I travel clockwise. But the important fact is I trace out the same unit circle. These are all parameterizations of this exact same equation. All I'm changing is the position on the unit circle at different times. Either of these parameterizations are totally fine, but you'd probably prefer this one because it's a lot more familiar to you. If I asked you where your location would be at 7 pi over 6 time, for example, you'd immediately know that it's over here. Whereas if I asked you where your location would be at 7 pi over 6 time on this parameterization, you might struggle to figure out that you'd be down here. And these aren't the only two parameterizations of this curve. In fact, there's infinitely more, and we can change to start anywhere on the unit circle and travel at whatever speed we want around the unit circle in whichever direction that we want. But all of that is way beyond the scope of our class. All I wanted you to see is we can go from the parameterized form of the unit circle to the standard form, and from the standard form back to the parameterized form. And when you're going from parameterized to standard, there's a harder way to do it, this inverse trig argument that follows the methods of the previous video, and there's a clever way to do it where you take advantage of the Pythagorean identity. When you're traveling in the other direction from the standard form to the parameterized form, there's infinitely many parameterizations that you can come up with, but the one that will be easiest for you is to let x equal the cosine and y be equal to the sine of t. That's a lot of theoretical stuff, a lot of justifications for these parameterizations, but you might wonder, how am I ever going to use this, or why did I bother learning all this? There really is a reason why. Let me show you. What if I gave you this parameterization? X is equal to 2 cosine of t minus 1, and y is equal to 2 sine of t plus 3. What if you were wondering about the graph that this parameterization represents? Well, you got options. One option is to keep track of the t and the x and the y and plot a bunch of points and try to get an idea of what the graph looks like. But another option would be to change this from the parameterized form to the standard form, and then take a look at that standard form and see if you recognize it as something we've already learned in this class. It'll turn out that you have. How do you go from the parameterized form to the standard form? Well, remember there's this little trick. We're going to take advantage of the fact that the sine squared of t plus the cosine squared of t is always equal to 1, this Pythagorean identity. I want to take these two equations and plug them into this equation. How am I going to plug these equations in here? Well, this is really just saying the sine of t squared plus the cosine of t squared is equal to 1. So if I could solve this equation for the cosine of t, I could plug it in, and then solve this equation for sine of t, I can plug it in. So let's solve those equations. If x is equal to 2 times the cosine of t minus 1, then x plus 1 is equal to 2 times the cosine of t, and therefore the cosine of t is equal to x plus 1 over 2. Similarly, if y is equal to 2 times the sine of t plus 3, then y minus 3 is equal to 2 times the sine of t, so the sine of t is equal to y minus 3 divided by 2. I've solved for sine of t and cosine of t, so I can plug those in here and get y minus 3 over 2 squared plus x plus 1 over 2 squared is equal to 1. I've gone from the parameterized form to the standard form. Wait, why did I do all that? Well, the idea is maybe you can recognize this as an equation that you know what the graph looks like. And you stare at it and you're like, nope, sure can't. I think you can. Look what happens when we simplify this a little bit. When I have a fraction squared, I can think about that as the top of the fraction squared divided by the bottom of the fraction squared. So instead of y minus 3 over 2 squared, I can think about it as y minus 3 squared over 4. Similarly, I can think about this fraction as x plus 1 squared divided by 4. And if you had this equation and you really didn't like fractions, maybe you'd think to multiply both sides of the equation by 4. If you multiplied both sides of the equation by 4, you get y minus 3 squared plus x plus 1 squared is equal to 4. Is this something that maybe you recognize? Maybe you could stare at this form and figure out the center and the radius. And actually the way it's written is a little bit tricky. It might be easier for you to figure it out if you wrote the x terms first and then the y terms. Remember, the number in the parentheses with the x gives you the x coordinate of the center, but you got to be a little bit careful. We have to change the sign. So the x coordinate of the center is -1 and the y coordinate of the center is +3. And then the number over on the other side of the equation gives you the radius. But again, you got to be a little bit careful. The radius isn't 4 or maybe 16 or something. It's 2 because the other side of the equation is always the square of the radius. Anyways, the point is that this equation represents a circle centered at -1, 3 with radius 2. -1, 3 is this point right here. Radius 2 would give me a circle going through these different points. It doesn't really look like a circle because my axes are a little bit skewed, but trust me, this really is a circle centered at -1, 3 with a radius of 2. The argument is, if you started out with this parameterized form and had no idea what the graph would look like, we can use the methods that we learned to rewrite it in standard form, taking advantage of the fact that once it's in standard form, we can recognize it as a circle and recognize the center and radius of that circle. It's worth pointing out that just like we can go from parameterized to standard, we can go from standard to parameterized. Remember, the trick for going from the standard form to the parameterized form is taking advantage of the fact that 1 is equal to sine squared plus cosine squared, thanks to my Pythagorean identity. So I can change the 1 in the standard form of my equation into sine squared plus cosine squared, and then stare at this equation and choose my parameterization. We can do that same thing down here. And you're like, no, that's not going to work because I have a 4 here. Well, that's true, but we can change this 4 into a 1 if we divide both sides of the equation by 4. Instead of y minus 3 squared plus x plus 1 squared equals 4, if we divide both sides by 4, we'd be back up at this line. Y minus 3 squared over 4 plus x plus 1 squared over 4 is equal to 1. And taking advantage of my Pythagorean theorem, instead of writing a 1 right here, I could write sine squared t plus cosine squared t. We're not quite at the stage where we can see the parameterization because this is not something squared, only the top here is squared. However, with a little bit of clever algebra, we can rewrite this as y minus 3 over 2 squared and rewrite this term as x plus 1 over 2 squared. And now on the left-hand side of the equation, we got something squared plus something else squared, which is the same as what we have on the right side of the equation, because sine squared t means sine of t squared, and cosine squared t means cosine of t squared. So now I can stare at this equation and choose my parameterization. I could choose to let sine of t be equal to y minus 3 over 2, or I could choose to let sine of t be equal to x plus 1 over 2. Either way is totally fine. However, as we've seen in the past, if we choose to keep the sines with the y coordinates and the cosines with the x coordinates, things work out a little bit nicer. So let's choose to let sine of t be equal to y minus 3 over 2, in which case the cosine of t would be equal to x plus 1 over 2. That's my parameterization. I'm done. Well, not quite. The parameterization should give you x in terms of t and y in terms of t. I need to solve these equations for x and y respectively. Fortunately, that's really easy. Just multiply both sides by 2 and then add 3, and we'll get that y is equal to 2 times the sine of t plus 3. And down here, if we multiply both sides by 2 and subtract 1, we get that x is equal to 2 times the cosine of t minus 1. Now we have our parameterized equations, which end up being the exact same ones that we started out with up here. Right, but why would I ever do that? I understand why I went from parameterized to standard form so that I could recognize this as a circle centered at negative 1, 3 with the radius 2. But why would I ever go from the standard form to the parameterized form? Well, I'd argue that the parameterized form is easier to come up with the graph of. If you stare at this form, you got to remember that we changed the signs on the 1 and the negative 3 to come up with the center. And it's the square root of this number that represents the radius. But over here, once you understand the parameterized equations, it's a little bit easier to keep straight. Think about what this is saying. The y coordinate is equal to 3. Here's where y equals 3. Plus 2 times whatever the sine of t is. Sine of t is what's going to change here, but the sine of t goes as low as negative 1 and as high as positive 1. So from this 3, I'm going to be adding on 2 times something that is as high as 1 or as low as negative 1. From this 3, I'm going to be adding at most 2 or subtracting at most 2. The y coordinate is going to get as high as 2 more than this 3 up here or 2 less than this 3 down here. What about the x coordinate? Well, I think about the x coordinate as kind of starting at negative 1. Here's where the x coordinate equals negative 1. And then from that negative 1, I'm going to be adding 2 times the cosine of t. Much like the sine of t, the cosine of t oscillates between negative 1 and positive 1. So 2 times the cosine of t will oscillate between negative 2 and positive 2. So from this negative 1, I want to add as much as 2 or subtract as much as 2. So I want to go 2 units to the left over here to negative 3 and 2 units to the right of negative 1 over here at positive 1. The solid lines will end up giving the center of my circle, and the dotted lines will kind of bound the perimeter of the circle. What I'm saying is from this parameterized form, we can immediately get the x and y coordinates of the center to be negative 1 and positive 3. And the radius of the center to be equal to 2. A little bit more straightforward than how we read this equation down here. This video ended up getting really long, but I think that's good because it's pretty complicated. What I want you to take from this video is, I want you to have the ability to go back and forth between the parameterized form of a circle and the standard form of a circle. And I want you to be able to read either of the forms and come up with their graph. And it would be awesome if you left with the realization that there's some advantages to having the parameterized form of the equation of a circle. For one thing, it's easier to read, but also it's kind of nice that it captures this idea of position and movement, which maybe you could see as useful in a different application. I think that's all that I have on parameterization, so I'm going to call this video good.